Hi, and welcome to 7.1 Tangential Velocity. This is the beginning of the circular motion unit, specifically objects undergoing uniform circular motion. And again, uniform circular motion is when you're moving in a circle at constant speed. However, your velocity is changing. Why is your velocity changing? Because velocity is a vector quantity. Vectors have direction. And as you move around in a circle, your velocity keeps on changing direction. So as you go around, this velocity vector continuously changes. So you continuously have a change in velocity. Anyway, here we go. Number one, it says an athlete in a hammer throw event swings a hammer in a horizontal circle at constant speed. Again, that tells us that it's undergoing uniform circular motion. The radius of the hammer's path is 2 meters as indicated here. Number one says, if the hammer is released at the position shown, it will travel towards point A, B, C, or D. As we just talked about, the hammer is moving around in a circular path. It has inertia. If it's released here, at this instant, right here, the inertia of the object wants to make it continue going in this direction. Its instantaneous velocity vector, you could call it, is pointing towards, as you could see, point B. So the velocity is tangent to the circle, meaning that it only touches the circle at one position here. And at this position, since it's going clockwise, it's going to go towards point B. If it was going counterclockwise, or some people from Britain say anti-clockwise, all right, it would be going in this direction, so it would go towards point D. All right, anyway, so the correct answer for 1 is B. 2, if it takes 0.84 seconds, so the time is 0.84 seconds, to complete one full revolution, what is the hammer's tangential velocity? As we talked about today in class, velocity is equal to the distance divided by the time. And in this case, since we're moving in a circle, we're talking about the distance around the circle. In other words, the circumference. The circumference is equal to the pi times the diameter, or 2 times the radius times pi. The equation people remember is 2 pi r. That's the circumference. Now we want the time for one circumference, the time for one cycle. In physics, we call the time for one cycle the period. It's the amount of time per cycle. So here it tells you it's 0.84 seconds for one full revolution. So in this case, they're also telling you what the period is. We don't have to figure it out. We could plug it into our formula. So the velocity is equal to 2 times pi times the radius is 2 meters divided by the period is 0.84 seconds for that rotation. So the velocity is going to be equal to around 15 meters per second. And it's very important, we're using pi here, so if you plug it in your calculator, just make sure you're in degree mode. We are not in radian mode for this. All right, so you get choice C. Number 3 says, compared to the speed of the hammer at the end of the rope, meaning this position right here at the end of the rope, the speed of the point on the rope at position A is, so here's position A. All right, so compare the speed at position right here and position A. Which one's faster? Well, as we talked about in class, again, this is a solid, we could think of it as almost like a solid object, this line right here. It's moving around the circle together. All right, it stays in a straight line. So that means this object's moving in a circle. It's not really an object. That point, and this point in a circle. Now, which circle covers the greater diameter? So this is the greatest circumference, the greatest diameter. So you're going to have the largest distance. All right, you have to cover the greatest distance in the same amount of time. So the time, the period, is the same for both A and B. Again, why is it the same? Because they're moving around together. You could almost think of it like this. So now these 2 points are moving around. They have the same period of rotation. They're constantly in line with each other. So since they have the same period of rotation, but on the outside over here, you have to cover a greater distance, you must be moving faster on the outside than you are on the inside. Point A is moving slower than the outside of the circle here. All right. So when it says compared to the speed of the hammer at the end of the rope, the speed of the speed of a point on the rope at position A is smaller. It's going slower. The speed is smaller. Okay. Number 4. In an experiment, a 0.05 kilogram rubber stopper is attached to one end of the string. So they're telling us the mass is 0.05 kilograms. That's not too important for us for this assignment, but tomorrow when we talk about centripetal force, we remember that the net force is equal to ma. That's Newton's second law. Well, I wonder, is the mass going to be important when we talk about the centripetal force? So it is when we talk about the net force. So we'll see how those are related. They're very closely related. It says a student whirls the stopper overhead in a horizontal circle, kind of like this, with a radius of 0.5 meters. The stopper completes 10 revolutions in 3.2 seconds. So the time is 3.2 seconds, not 3.3, 3.2. But the period, we don't know it yet. They tell us it's 10 revolutions in 3.2 seconds. I wonder how much time it takes for one revolution. Here, 10, and you could call it revs, revolutions, cycles, whatever you want, circles. All right. It says what is the period of rotation of the stopper. That's good. We were going to have to figure that out first, and then we figure out what the speed is, and then we can answer this question: is the velocity changing? So the period, there's a formula for the period, but it's not in your reference table. It's equal to the time per or divided by the number of revolutions or cycles or circles. All right, so the time in this case is 3.2 seconds. The number of revolutions is 10 revolutions. Now that doesn't really have any units, so when you do some unit analysis here, you have a second divided by nothing, all right, or you could think of a second divided by a 1. So you're left with seconds for the period, which makes sense because the period is the time for one cycle. So you do this division and you end up just having to move the decimal point over. You get 0.32 seconds is your period, and that means it takes 0.32 seconds to go around this circle one time. That's the definition of the period. How much time does it take for one cycle? So good. That's part A. Part B says what is the speed of the rubber stopper? We want to use that equation, 2 pi r over the period. That's the distance divided by the time. That's going to give you your velocity. The magnitude of the velocity is the speed. So 2 pi r, the radius is 0.5 meters, and the period we found, it's 0.32 seconds. So the velocity is about 9.8 meters per second. Nice, 9.8. That might be a familiar number. You should be very happy when you see that number. But it is not the acceleration due to gravity on Earth in this case. This is your tangential velocity, how fast you're going, not a rate of change of your speed like acceleration. All right, it just happens to be 9.8. So good. That's B. C says, is the velocity changing? How do you know? What do you think? Is the velocity changing? It is not changing. What if I told you that? The velocity isn't changing. No, I'm just kidding. It is. The velocity is changing. Even if the speed is constant. Well, how could that be? How is the velocity changing? Remember, velocity is a vector. Vectors have magnitude and direction, whereas speed is just the magnitude. So even if this thing has a constant speed, we're talking about the direction changing. You're moving in a circle. At this point, it's here. At this point, the velocity vector is going this way. Now we're going in this direction. The velocity vector is continuously changing the entire time. All right, so the direction is constantly changing, so we must have a changing velocity. All right, velocity changes, yes, changes direction. Very good. All right, moving on. Next page, number 5. A car makes one complete trip around a traffic circle in 5 seconds. Yes, that means the time is 5 seconds. But if you're a savvy physics student, you know you're making a trip around a traffic circle. It even says circle, so you know you're talking about circular motion. They tell you it takes for one complete trip, it takes 5 seconds. Not only are they telling you the time, they're telling you the period. That's the period of rotation, 5 seconds for one cycle. The speedometer on the car says it's traveling with a speed of 20 meters per second. So the velocity, the magnitude of the velocity is 20 meters per second, the speed. What is the period of rotation of the car? Oh, we already did that. All right, but if you wanted a formula, it's the time per the number, the amount of cycles. You could plug in what it tells you. The time, the period is equal to, it says 5 seconds for one cycle. So we already kind of did it in our heads. Like I said, we're savvy physics folk. All right, so this is 5 seconds for the period. And for B, what is the radius of the traffic circle? Good question. How the heck are you going to figure this out? Well, we did the guess method here. We wrote our givens down. We have our unknown. All you need is an equation. So you look in your reference table, and this one's not there. 2 pi r over the period. So you better write it in, or on the back of your hand. If you don't have a reference table, better cheat. No, you could remember it. It's just the distance divided by the time. You should technically be able to figure this out on the fly because you're moving in a circle, right? So what is the distance that you traveled? It's equal to the circumference of the circle. So the distance is the circumference. Got that. And how much time does it take for one circumference? That's going to be your period, which we just calculated. So no, you don't have to cheat. You should figure it out. You know the definition of the velocity, distance divided by the time, and we're off to the races. So you're looking for the radius here, and the period is 5 seconds. Oh, you know what I didn't plug in? The velocity. That's why we wrote it down on the side. Come on. Now we're in the substitute phase. So you substitute what you know, and you solve for what you don't. So 2 pi r is equal to 100. So pi r is equal to 50. And the radius is equal to 15.9, about 16 meters. That's the radius of that circle. All right, very good. Number 6, last one. All right, it says a 500-gram toy train. So the mass is 500 grams. Do we like grams? No, we like kilograms. We're not going to need in this case, but it's good habit to 1, 2, 3 places to the left. So that's 0.5 kilograms. Good habit to just change the grams into kilograms. And so a 500-gram toy train completes 10 laps of its circular track in 1 minute and 40 seconds. So, okay, they're giving you a lot of different units here. The number of revolutions, not Ray, we're not watching Star Wars. Number of revolutions is 10 laps. Or 10 revs, if we want to be consistent with what we did before, revolutions. All right, and the time for that is 1 minute 40 seconds. Go ahead, plug that into an equation. I'd like to see you try. What are you going to do, 1.40? No, come on. You got to convert this into seconds. You know 1 minute is 60 seconds plus 40 seconds. So this is equal to 100 seconds for 10 revolutions. This is not the period. We're going to have to calculate it first. It says the diameter of the track. Oh man, they're really messing you guys up. This is 1 meter. Do we like diameter? We don't care about the diameter. We want to know what the radius is because, that's what our formula says. It says V is equal to 2 pi r over the period. So you could do, the diameter. If this is 1 meter, what is the radius? It's half of that, 0.5 meters. Or you have to remember, where did this 2 pi r come from? That's just the circumference for the circle. So if they give you the diameter, you technically could do pi d, because c is equal to pi d. And I'm pretty sure, I don't know. Well, actually, I think in the reference table it says 2 pi r. Either one will suffice. It all works out because the diameter is twice the radius. But we're probably going to rock the 2 pi r equation here. And let's see. It says, what is the period of the train's rotation? It even tells you in bold. You got to convert it to seconds, people. So the period is equal to the time divided by the number of revs or cycles or circles, what have you. So the time is 100 seconds, not 1.4 seconds or anything crazy like that. You got to make 1 minute into 60 seconds and then add the 40. All right, and then it says 10 revolutions. So the period is going to be 10 seconds. If it takes 10 seconds for one cycle, it takes 100 seconds for 10 cycles. All right, so now we know what the period is. This is for A. And B, you already wrote the equation. What's the speed? The speed is just the magnitude of the velocity. So we're really looking for the velocity. It's equal to 2 pi r, 0.5 meters. Or you could just do pi times d, which would be just 1 times pi. So you're basically doing pi divided by 10. So we could do it in our heads. Works out to 0.314, yada, yada, yada. We'll put it like that for now. Meters per second. All right. Yeah, that's not significant figures. It'd technically be like 0.3. All right. Or something like that. Anyway, that's your answer. And have a good day.